Computer Systems, A Programmer's Perspective Textbook Review. Today we will be reviewing Chapter 2. Let's get started. Section 2.1, Information Storage. So how does a computer store data? It stores it using the binary system. What is the binary system? Well, we at least here in America, but most of the world use the decimal system, which is base 10. So that means essentially when you get to the number 10, you can think of it as starting over, right? Then you go 11, 12, right? The second the tens place, or sorry, the ones place like starts incrementing, and then once you hit 20, the tens place increments once, right? So a binary system just does the same thing except it's base 2. So you have, for example, 0 is 0, and then 1 is 1, and then 2 is 1, 0. Because now that you've reached the maximum of the system, the base, you have to move over into the twos place now. So now it's 1, 0. Increment again, 1, 1. Increment again, 1, 0, 0. Right? So that's how the binary system works. And each place is a bit, and a byte is 8 bits in a row. The hexadecimal system is a base 16 number system. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A is 10, B is 11, and C, D, E, F, and then that's 15. And then at 16, you start over again, right? Does that make sense? So now the conversion, the reason why we have the binary system is of course because it is helpful to think in terms of this or that, true or false, an electric current being positive or negative, a magnetic pulse going one way or the other. And it's useful to have the hexadecimal system, not only because you can represent insanely large numbers in a more concise format because it's base 16, so everything amplifies very quickly, but it is a really easy conversion from binary to hexadecimal. And the conversion is basically every 4 bits you figure out what the numeric value is. So let's take the 4-bit string 1010, right? So what is that? That's 0 in the ones place, right? And then 1 in the twos place, so that's 2. 0 in the fours place, that's 0. And then 2 in the 1 in the eights place, right? So 8 plus 2, that's 10. So 1010 is equal to 10. And in hexadecimal, that is A, right? A stands for number 10, the number 10. So, and you simply replace every 4-bit string with a hexadecimal number, and boom, you have your conversion. And if you know the bit vector or string, bit vector is just a series of bits. The same thing as bit string. So if it isn't divisible by 4, in other words, let's say you only have 3 bits, right? You just pad the rest of it with 0. So it'd be, let's say you have the 3-bit vector 110. Now it's 0, 110, right? It doesn't change the value, but now you can work with 4s, and it's the easy conversion. So you always pad the left-hand side. Okay, so bit vectors is just a series of bits. Bit shifting is when you want to shift a bit vector by a certain amount. So let's say we had the 4-bit vector 1010, okay, and we perform a left shift of 1. So that means everything gets moved over 1, right? So however, you don't now have a 5-bit string. You still have a 4-bit vector, but the 1 is just gone now. So it was 1010. Everything gets moved to the left, so 1 gets disappeared. Now that's 0, 1, 0, 0. and then zeros come in on the right. And you could also shift the other way. And eventually you'll see there are two types of shifting, and that is a logical shift and an arithmetic shift. Because when you do a, more specifically, a logical right shift or a arithmetic left shift, and just to give you a just to let you know what's coming, eventually we're gonna use the binary system to represent negative numbers, and we're gonna do that using a 1 in the beginning of the bit vector. So when you shift to the right, an arithmetic shift, would be on the left. It's coming in with ones. You're putting ones in, and then a logical shift would be you're putting in zeros. All right. So masking is first. Let me go over Boolean algebra because masking is dependent on it. So Boolean algebra is basically propositional logic, but with ones and zeros. So where 1 stands for true and 0 stands for false. So 1 and 0, in other words, true and false, is false, right? True and true is true. So 1 and 1 is 1, right? And it's the same thing with or, exclusive or, right? Just look these up. You could look up basic propositional logic in what's called a truth table. So just look up basic truth tables, and you'll see, oh, true and false is false. False and false is false. False and true is false. True and true is true. So out of the 4 combinations, there's only one in which the AND operation results in true, where both operands are true. And, true is synonymous with 1 and false is synonymous with 0 when it comes to Boolean algebra. And if you ever get into the design of the ALU, the arithmetic logic unit, which is the brain of the CPU, basically the thing that executes all the instructions, addition, multiplication, and everything, all the executions and how it executes an instruction is dependent on Boolean algebra. So addition is implemented using a series of ands and ors and stuff like that. Okay, so masking is when you and 2 bit vectors together, but more specifically, a certain type of bit vector. So let's say you have two 8-bit vectors, okay? So one of these vectors is going to be it doesn't matter, but let's just say 1, 0, 1, 0, 1, 0, 1, 0, okay? And then the other bit vector is going to be 0, 0, 0, 0, 1, 1, 1, 1. And when you AND these together, you're only going to get the 4 bits in the, whatever the 4 bits were in that first string, in the 1, 0, 1, 0, 1, 0. So the result is 1, 0, 1, 0, right? Because everything to the left of all our 1s are now zeros, because whatever and false is always false, so always 0. And then 1 and whatever is going to be the whatever, right? If it's false, it's false. If it's true, then it's true. So this is a way to, if you just want to see the bits in a certain part of the string, right, you can AND it with another bit vector where wherever you want to see those bits, you put 1, and the rest of the string you put as 0. And that's called masking. Okay, so virtual memory, we went over this, but virtual memory is just a process's view of the memory, just as this monolithic array of bytes. It's just an array of bytes, and each byte is an address for memory, where you can store 1 byte at. So the virtual address space is this array of bytes. Now, they store words. Sorry, not bytes. It's an array of words. And it depends on the, the virtual address space. The addresses, the computer will work on some fundamental size of a bit string. Usually, today, it's either 32-bit or 64-bit. And this is what a word is. So a word is either going to be 64 if it's a 64-bit processor, or 32 if it's a 32-bit processor. And that's how the addresses work. So you also have little, big, or bi-endian. That is, whoops, hold on, let me charge my laptop here. Okay, we're good, sorry. So little endian is when you're putting in a bit vector into, or let's say 2 bytes. When you put in 2 bytes into the memory, it gets stored in with the least significant bit, so the furthest right bit, or byte, I should say, first, and then the next least significant byte next. And so if you're reading these out from like memory in reverse order, you would essentially get the bit vector in reverse order. And then big endian is when you put the most significant bit first in memory, or sorry, most significant byte first in memory. And bi-endian is when the hardware gives you the choice to do either, and essentially the operating system will choose for you. Now, unsigned encoding, 2's complement encoding, and floating point encoding are all data formats. So we have the float, signed integers, and unsigned integers. And in order to represent those, we have to encode the binary a certain way. So we'll get into that in the next section. Overflow is when, when your machine works with a certain amount of bytes. Let's say it's a 32-bit machine, so it works with 4 bytes, right? And you do a adding operation that is bigger than, so let's say, these 2 bits, 1, 1, you add with 1, 1, but you can only work in terms of 2 bits. Then you can't store the result of that calculation because you only have 2 places, right, to work with, the 1's place and the 2's place. So essentially, like, part of your answer is overflowing. That's what it's called. String representation. So a character is usually represented with 1 byte on most systems, and it in memory, you store 1 byte at a address location, the address being the word of the machine. So that's how long it is, a word for an address. And so how it would work is, let's say you want to store the string hello world. Well, there's the H character, the E character, yada yada. So what you do is, and each character is a byte, right? So you put the H byte in there, and then you put the E byte after in the next memory location, then the L, then the other L, then the space, then you keep going on, and then usually a terminating character at the end of the string to let you know that you're done with 1 data segment. So that's how strings are represented in memory. Lastly, binary isn't portable. Of course, each machine, because we'll have different, we'll look at binary in a different context. They'll think this one sequence of 1's and 0's does something else, while another machine might think it does another thing, right? Because they're all made by different companies, essentially, and different programmers. And lastly, since the word size of the computer is what you use to address items in memory, right? It can be, if you use it, it can make your software not as portable, because if you're using an integer as a pointer, right, it could be a different size on different machines. It could, and then you're going to get different answers when you're pointing to things in memory, because an integer could maybe be 4 bytes on one machine but 8 bytes on another. Usually the integer is the size of the word on the machine, by the way. So if it's 32-bit machine, 4 bytes, usually your integer size is going to be 4 bytes as well. Lastly, you can encode finite sets with bit vectors, of course. And how you do this is, let's say you have the set 0, 3, 4, right? Where 0, 3, 4 are the elements of the set. You can essentially represent this with a, let's just say a binary set. And what you do is you do, okay, there's a 0 in there, right? So we're going to put a 1, and then comma, there's no 2, so that's a 0. There's no 3, that's a 0. There's no 4, that's a, or I think there I said there was a 3, that's a 1. There's no 4, that's a 0. There's a 5, that's a 1. So you're just writing out every single number, and if the number is in the set, you write a 1 where that number is, and then if it isn't, you write a 0. So, let's say you only have two numbers in a set, namely 1 and 21, you're going to have 22 members of the binary set that corresponds to it, right? Because 22 because you have to go to 21 and there's 0, because you have to represent 0, 1, 2, 3 all the way to 21 just to say that the 1 is included and the 21 is included, but nothing else is. And when you have these binary sets and you apply Boolean algebra to them, they're essentially set operations, by the way. Or the Boolean the Boolean operators like and now turn into union. That's what they represent conceptually. When you and two binary sets, it's going to be the same result as union. Same with intersection, and or would be union. Okay, section 2.2, integer representations. So these 4 formulas right here are from the book. I claim no credit for them, although I would imagine I'm allowed to put them on here just because they're so universal. So B2U means binary to unsigned. B2T means binary to 2's complement. I'll explain what that is in a second. And T2U means 2's complement to unsigned. U2T means unsigned to 2's complement. And these functions, B2U and B2T, are a bijection, by the way, and that means there's a 1-to-1 correspondence between all inputs and outputs, which you would hope for in a function that shows you how to add numbers. So let me explain these formulas right here. So how we represent an unsigned number is really straightforward. We just use the binary system. So what this formula is telling us is let W be the length of the bit string. So let's say we have 4 bits. So 4 is W, right? And then I is going to be each place in the bit string. And we're starting with 0, right? So first we say what's in the 1's place, or where I is 0. So the first bit. And then we say, oh, it's, let's just take the bit string 1010. It's 0, okay? So we do 0 times 2 to the 0, which is 0, obviously. And then we do that for the 2's place, the 4's place, and then the 8's place. And then that's basically how you would convert a binary unsigned representation to a unsigned number. Lastly, we have binary to 2's complement. Now, what is 2's complement? 2's complement is a way of representing signed numbers in the binary system, and that's basically the most significant bit is a 1 if it's the number's negative and a 0 if the number's positive. So 1010, that would be a negative number, and I'll share with you how to add it right now. So let's say 1010, okay, is our 4-bit number. First, the leading 1, right, represents the 8's place. So that would be 8. However, since the number is negative, we always make this leading number negative. So negative 8, and then all the other bits are treated as positive. So it's negative 8 plus, so I think I said 1010. So negative 8 plus 2 is negative 6. And that's how we represent signed numbers. If you work with these or do a few practice problems or look it up, it's pretty hard to explain over voice, right? Because I'm essentially explaining math formulas. But if you do it on paper and work it out, you'll find it's very straightforward. And to explain this formula, what it's saying is on the right-hand side with the summation, the sigma notation, it's saying add up just like you did the unsigned numbers all the way to the last bit. And then make the last bit, like add it up like a or times it by 2 to whatever, it should be times by, which is w minus 1. So in our example, it would be 3, right? 4 minus 1 is 3, so 2 to the power of 3 is 8. Times that number by 8, which is 1, and then make it negative, and then add it like that. So that's 2's complement. Okay, so the ranges of unsigned and signed. So one interesting thing to note is the unsigned range is from 0 to whatever the maximum number is, which would be all ones. And the unsigned, the signed, how it works is the minimum, right? Because we have negative numbers, it won't just be 0, is going to be 1, 0, 0, 0, 0. Because if all those zeros were 1, they would be added to that big negative number and be, making it less negative. So 1 with as many zeros as possible is going to be your minimum number, and then 0 with as many ones as possible is going to be your biggest positive number. And an interesting thing to note is there's one more negative number than there is positive numbers, so the range isn't symmetric around 0 in 2's complement, because essentially the biggest place, like the most significant bit, is the signed bit. And 1, 0, 0, 0, 0, whatever, is always going to be 1 bigger than 0, 1, 0, 0, or 1 bigger than 0, and then a bunch of ones, right? For example, 1, 0, 0 is 1 bigger than 0, 1, 1. Another example, 1, 0, 0, 0, 0 is bigger than 0, 1, 1, 1, 1. It's always going to be that way. So that's why it's unsymmetric. And as a result of these two ways of looking at these two different things, when you cast, which means basically it's a conversion from one to the other, you're going to get weird results, right? Because an unsigned number has let's say you get 4 bits for unsigned and 4 bits for signed, which is 2's complement. You can represent a bigger positive number with an unsigned 4-bit representation than you can with a 2's complement. So when you're converting, you're going to get a negative answer most likely. For example, 1, 1, or 1, 0, 0. So that's 3 bits right there. In unsigned version, that would be treated as 4, right? But in an assigned treated version, so 2's complement, that would be treated as negative 4, because the first bit is negative. The most significant bit is negative, right? So you have to be careful when you're converting, because the binary isn't changing. It's just the way you're looking at it. That's what casting means. The underlying data is staying the same, but the way you're looking at it changes. Okay, so zero signed extension. So, there's also casting not only between signed and unsigned, but bigger data types and smaller data types. So if you cast down to a smaller data type, let's say you had 8 bits to work with, now you have 4, essentially those most significant 4 bits just get removed entirely. So you obviously, if they weren't all zeros, your number is going to change. However, if you cast up, so you were working with 4 bits, now you can work with 8, your number is always going to remain the same. However, it depends how you do that on 2's complement, right? You can't just add in a bunch of zeros. Instead, you have to add in a bunch of ones, so you keep the sign consistent. Alright, so that's it for how integers are represented. We'll see how floats are represented in the last section, but moving on to section 2.3, integer arithmetic. So again, with all this stuff, I encourage you also to not really pay attention to these formulas, but you can refer to them, but try and understand why they are the way they are. And I'm going to try and explain that to you, but again, it's going to be hard because I, am just using my voice and not a pen and paper to do this. So now, what's interesting is unsigned and signed. By the way, from now on, I'm going to be saying like signed and 2's complement is synonymous. So unsigned and signed numbers, they actually have additive inverses. Now, with the signed thing, it's obvious, right? Because it's signed. So like -4, you can just add 4. That's its additive, +4. It's its additive inverse. However, additive inverse just means adding another number to get to 0. And then, however, with the range isn't symmetric around 0, so the biggest number is, or there's one more negative number than there is positive number. So what's the additive inverse to that? It's itself, because when they get added together, there's going to be an overflow. And within that place, there's now going to be 0. And then the place that doesn't actually show, there's going to be a 1, but it doesn't show, right? Because it gets overflowed out of how many bits you're working with. So its additive inverse is itself, the biggest negative, or the smallest negative number. Or the smallest number. Now, with unsigned, the additive inverse is just however the maximum signed version it could have, or unsigned number it could be within the bit representation, minus the desired number. So let's say you have a 0, 0, 1, right? So what does that equal? That equals 1. What's the biggest number you can get with 3 bits and an unsigned encoding? That's going to be 1 plus 2 plus 4. That's 7. So 7 minus 1 is 6. 6 is 1's additive inverse when you are working with 3 bits. And 6, represented as binary, is going to be 1, 1, 0. And it's because when you add 1, 1, 0 with 0, 0, 1, you're going to get a, sorry, I said that incorrectly. But when you add the remainder, right, of the biggest thing it can get, you're going to get an overflow. So basically, in additive inverse, you're just looking for an actual additive inverse if it's a signed encoding, or an overflow. And an overflow where everything else is 0, right? And with signed encodings, you could actually have a positive overflow or a negative overflow when you're adding 2 numbers, right? Because what happens if in a signed encoding you're working with 0, 1, 0, where that first most significant bit is the signed bit, and then you add that, so 0, 1, 0 with 0, 1, 0, the answer is going to be incorrect because you ran out of the range for positive numbers, right? That number is bigger than 3 bits can handle for a signed representation. So what's going to happen is you're going to get what's called positive overflow. And this formula on the screen here, x plus y minus 2 to the w, is saying with that overflow, this is the number that you're going to get, like the normal number, right? It's going to be an incorrect operation, but and the way it does that is because so in this case, 0, 1, 0 added with 0, 1, 0 normally is just going to be 1, 0, 0, but that's now a negative number in a signed encoding. And what that is equal to, that negative number is equal to -8, but the original 2 numbers were 2 and 2. So when you add those, you get 4, right? But see how our answer is now -8? So how does that work, right? Well, that's because of, it's overflowing, and it'll do the same thing for negative numbers, except it'll overflow in the place next to the signed bit. Multiplication is just a modular arithmetic. Basically, you're just multiplying and then modding by the total number, 2 to w, which w is the length of the bit vector. And that's just a way of getting only the things that didn't overflow, essentially. Okay, so last thing, floating points. So float representation, you have a sign, an exponent, and a mantissa. And what that means is floating point is represented as blank, which is the mantissa. So mantissa times 2 to the exponent. And the mantissa is signed, and that's the sign bit. So you'll have 1 bit for the sign, so 0 or 1, and then let's say like 5 bits for the exponent. And then you'll have 15 bits for the mantissa. And if the way it works is if the exponent bits aren't all 0, then you imagine a 1 in front of the mantissa. And what the mantissa is it's the numbers after the decimal point. So essentially, if the exponent is bigger than 1, you have 1 dot mantissa, whatever that is, times 2 to the exponent. And if the exponent is all zeros, then it's just going to be 0 dot mantissa times 2 to the exponent. And all of that, remember the sign bit too. So normalized is when the exponent is not all ones and not all zeros. Denormalized is when it is all ones. And infinity and NaN are special circumstances where you'll have maybe the mantissa is all zeros, or the exponent is all zeros, or the mantissa is all ones and the exponent is all ones, or the combination of those. Okay, so every system implements rounding differently with the mantissa. Sometimes you'll be rounding, each system will pick a different rounding method, or it may not round for you at all. So when doing arithmetic operations. Floating point operations, so I just covered that. Well, sort of. The way arithmetic operations are done with floating point numbers is you just work with the mantissa, and then basically first you try and get the exponents to be the same, and then you could just straightforwardly work with the mantissas. And yeah, so casting is an interesting case because it's not like the other things. The binary number will actually change, and how it's going to change is it's basically just going to calculate whatever the number is the floating number represents. So let's say it's 3.4456, and if you're casting to an integer, signed or unsigned, it's now just 3. You just cut off all the decimal points, and that's what casting is. So this is the end of the video. I'm sorry I couldn't explain this in more depth because it's very hard without a paper and pencil, but luckily this isn't too fundamental to the book, and all you really need to know is sort of there's different ways of encoding signed, unsigned, and floats, and when you cast and there's ranges for each of these, right? So when you're casting and even doing arithmetic, there's times where you're going to get wrong answers if you're not using the ranges of these numbers correctly. And what I forgot to mention is there is a limits.h file in the standard C library, and that shows you all the ranges of these different types of numbers. So make sure to look at that, and also make sure to look at make sure to actually do examples on a piece of paper with converting binary to hexadecimal, truncating bits, extending bits, shifting, everything mentioned in this video. So thank you for watching, and make sure to subscribe to see the rest of this book. It'll be much easier to explain the rest of this book because it's not a math book. This is the only section that covers math. So yeah, and make sure to leave a like and a comment, and I'll see you in the next video. Thank you.